welcome for this series. So Krishnendu, is all yours.
Yeah. Okay. Thank you, Sudipta. So in the last lecture where I left, oops. Why is it not? Hold on. Okay. Page up. Yeah. So in the last lecture where I left, we looked at this, single layer or monolayer graphene, and we found that the density of state varies linearly with the energy around the Dirac point because it's a linear function, and there is this property of helicity associated with the Dirac electrons at k and k prime points. Now these are going to stay with us for some time. So not only in context of graphene, but also in context of topological insulators, which I'm going to hopefully address on Friday. So let's see. So now I'm going to take a slight digression and talk a bit about topics which I'm not going to further cover in this course, okay? But they are reasonably important part of the literature, so I'm just going to briefly mention them. Okay, so two topics in particular. One of them is about multi-layer graphene, that is if you have a bilayer or other things, what happens. And the second one is about the interaction effects in graphene. Okay, both of them are something that I'm not going to cover at any rate. So, so just a digression, I also got requests from participants asking for reading material. So I'm going to give them to Sudipta along with this lecture PDF so that he can circulate this to all of you. Okay, so just hold on for a second. Okay, so bilayer graphene are two stacks of graphene honeycomb lattice placed on top of each other. Now clearly there are different choices here. First is that I can take the second layer, which is right here, and put a sublattice of the second layer over a B sublattice of the first layer. Or I could put a sublattice of the first layer, which is given by A1, over an A sublattice of the second layer, which is given by A2. Okay. Now, when I stack it in such a way that, A is over A, so to speak, this is called an A stacking, okay, and otherwise it's called an AB stacking. There are several other possible stackings if you increase the number of layers, such as AB, 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 which is typically called the Barnell stacking, or others, okay, which I'm not going to talk about. But let's just look into this bilayer thing. So suppose I now want to write down a lattice Hamiltonian, a tight binding model for this bilayer, and I'm going to look into this AB stacking, which is more common thing to find in nature. So you see that I'm going to get an interplane hopping, which is this gamma naught, which was T in my previous discussion. But then I'm going to have a hopping from one layer to another, which is directly on top of it. Okay, so between 2 points, which is directly on top of each other. So you could have, so for example, if I take this particular A stacking, then this would be, well, if I take this, whatever, AB stacking or anything like that, I'm going to get a A1 dagger and A2, okay, hopping like this. And I could get a dagger B, stacking if I just consider the next nearest neighbor. Okay, so they're going to have gamma 3 and gamma 4. So that's roughly the tight binding model. Now the point is that suppose I ignore gamma 4, which is the hopping between this B1 dagger and B2 dagger. Okay, and I could just keep gamma 1, gamma 3, and gamma naught. Okay, then you would see that there is a V which depends on this gamma 1. V, which is an external applied potential that I could put, and then there are terms which depends on gamma 1, which is the hopping between 2 layers, and gamma 3, which is the hopping, which is sort of the off-diagonal hopping between the 2 layers because it connects A to B. Okay. Now the point is that for small gamma 3, in the limit when this gamma 3 is small compared to gamma 1, which is typically the case in this case of bilayer graphene, I can integrate out this gamma 3 and get an effective two-layer Hamiltonian for this graphene. In fact, it's not really a two-layer Hamiltonian. What happens is that you diagonalize this for any gamma 3 and gamma 1. Numerically, you can always do that. And you find that when V is 0 and gamma 3 is 0, you typically have 4 bands. Okay, 2 of these are far apart, whereas the other 2 are close to each other. Then you reason that if you just want to look at the effective low energy band, which is the bands which are near this Fermi energy, then you are going to just look at these 2 bands. Okay? And effectively, these 2 bands have a dispersion which depends on k square and not k. So this is a quadratic band touching that you have and not a linear band touching of graphene. And that comes because of the fact that now you have these 2 layers and only a gamma 1, because I have set gamma 3 to 0. And if you just take this, if you just put gamma 3 equal to 0 and take this gamma 1, in the limit where, this gamma 1 is small compared to this VFK, you are going to get a quadratic dispersion. Okay. So these bands touch at some k equal to 0, or k equal at the edge of the Brillouin zone at capital K, that is. So this is the deviation from the edge of the Brillouin zone out here. But they touch in a quadratic manner, and this is a big difference with the center graphene. And this is the general dispersion that you have, which is given in the bottom of this stuff. But more importantly, when you put in a V, that is an electric field between these 2 layers. Okay, so you put in an electric field, which means you have opposite between the layers, which means you have opposite V or voltage drop across the layers. So if one of them is V, the other one is taken to be minus V, and that's just a choice. You open up a gap. Okay, so this means, and this is extremely important from a technological point of view, that you can tune these band gaps in bilayer graphene by using an external electric field. Okay. And this has enormous implication for application to LED physics, where you want to generate light out of this graphene stuff. I'm not going to get into this, but this is an important property that one should know. Okay. So bilayer graphenes can have band gaps which can be tuned by an electric field, whereas that property is not there for single layer graphene. And then instead of bilayers, you can have 3 layers, 4 layers, multi-layers, and you can do the stacking, calculate the energy dispersion, and one can get different features, but I'm not going to get into that. Okay, so next, what I'm going to do is that I'm going to move into the role of interaction. Now, first of all, I have told you when I started this graphene thing that I'm going to consider non-interacting electrons. But the first thing to note is that, is this non-interacting electron a really good description? Well, the answer is actually no. And why is this the case? One can understand this. You see, graphene is a Dirac material. What does that mean? That the low energy dispersions of this graphene typically has a Dirac-like dispersion. But if we just step back for a moment and think of this Dirac theory, which is this theory of electrons interacting with photons, well, that's not explicitly in the Dirac equation, but really Dirac theory is a manifestation of electron-photon interaction, right? That's the standard QED for you. Now, if you think of QED, so it's of course a perturbative theory. You can get enormous insight into the theory just by doing perturbative physics, and that's your Feynman diagrams and the insight developed by Feynman and Schwinger and Dyson and others. But why is it a perturbative theory? Well, the reason is that it is perturbative because there is a dimensionless coupling, which is called the fine structure constant, which is given by E squared divided by H bar C, and that's 1 over 137. That's your expansion parameter in this thing. here we can find out a typical expansion parameter of that sort. You see that the typical kinetic energy of a Dirac electrons in graphene sitting near the K band, okay, is E square over is h bar Vf times capital K, where capital K is the wave vector compared to at the edge of the Brillouin zone, and that's roughly 1 over the lattice spacing. Okay, the interaction, of course, if I take just a Coulomb interaction, which can be screened or non-screened, I don't want to get into the details of that, but the point is that if I take interactions, then interaction goes as E square over A. Okay, where A is again roughly the lattice spacing, and this is of course up to constants of epsilon naught for 4 pi epsilon naught or whatever system of units you take. But the point is that if you take the ratio of these two, you get E square over h bar Vf. Okay, so that's the ratio between the potential energy and kinetic energy. Now the point is that Vf is roughly 100, the Fermi velocity of graphene, that's roughly 100 times of the speed of light. So this quantity, so this quantity alpha, which is given here, which comes from this kind of consideration, essentially is, okay, I haven't written the h bar here because I have set h bar to 1 in many of these calculations, but that's what it is. Okay, so E square over h bar Vf, taking epsilon not to be 1, it's a number anyway, order 1. This is 1 over 137 times C over Vf. That is the ratio of speed of light to the Fermi velocity of graphene. Now, what is this ratio? This ratio is close to 100, it turns out, okay? Because the Fermi velocity of graphene, of electrons in graphene is roughly 100 times the speed of light. So this means that alpha, instead of being a really small number of 1 over 137, now becomes a number which is close to 0.6 or 0.7, something like that. 100 by 137, okay, you do the math. It's 0.7, most likely. 100 by 140 is like 5/7, that's like 0.7, okay. But the point is that it's a sufficiently strongly interacting theory of electrons, okay. But we are taking this theory as if it's non-interacting, and why can we do that? It's with the assumption that just as electrons inside a metal is represented by Fermi liquid theory, which tells us that the interaction, of course, is present and it's a very important component of the ingredient of your theory, but all it does at the end of the day is to renormalize certain parameters of the theory, and you can still talk about free fermions in a metal, right? And the reason that happens is that Landau's Fermi liquid theory tells you that what electron-electron interaction does is to sort of denormalize things like the velocity, Fermi velocity of the electrons, or other quantities, the effective mass and stuff like that. But it still leaves the quasi-particle picture intact. If you excite these fermions, you still get particle-like excitations, okay, with definite charge and stuff like that. Now the question is, does this hold, okay, for graphene? And one important difference between graphene and these fermions in a metal is that in graphene, near the Dirac point, you lose density of state. So there are not enough electrons to screen Coulomb interaction, so that electron-electron interaction is effectively long. So one doesn't really know before doing the calculation whether this is going to hold on. And this calculation has been repeated in several ways by several people, and it's by itself a huge subject. And I'm not going to get into the complete details of that. But what I'm going to tell you is basically that if you do a perturbative calculation, taking 0.7 to be still a small number, you find that your Green's function now has self-energy correction due to electron-electron interaction. And when you aim to calculate those self-energy corrections, and these are the Feynman diagrams which are involved, okay, this gives rise to, so this sigma 1 is the first order correction and sigma 2 is the second order self-energy correction. So for example, sigma 1 is this bubble, and sigma 2 as B, C, and D, the three other bubbles. This is a standard self-energy correction that comes in. You find that there is a log divergence that comes in, okay? And the reason it comes in is the nature of this Dirac theory. You see, there needs to be an upper cutoff because in graphene there is a lattice, and this Dirac theory only holds for a range of momentum or energy around the Brillouin zone, edge of the Brillouin zone, but it really doesn't hold to all length scales or all energy scales, okay? So you put in a cutoff, and it's only within this cutoff that your theory essentially gives you good results, okay, reasonable results. And this cutoff is roughly the energy point at which the lattice energy starts to show deviation from the standard linear Dirac dispersion. Okay, so if you draw these bands, which we did at some points, so if you draw these bands out here, you see that around this Dirac point, it continues for some time, and then it starts to bend, okay? And this bending, which is roughly about an electron volt, or maybe 2 electron volts from the Dirac point, is the cutoff energy above which this Dirac theory is not going to work, okay? And this cutoff energy is always present, and k by lambda is a small number, which means that you have a logarithmic divergence of several quantities that comes in from this Dirac theory. This divergence doesn't occur if you do this calculation from a lattice theory, but it's only an effective low energy behavior. Okay. Now the point is the following. Now using this and some other renormalization group techniques that people typically use for people who are familiar with technical aspects of this, it's a large N RG calculation where N is the number of components of electrons, and in graphene it's 4 times, okay, so it's 4 because you have valley and spin degrees of freedom. Okay. So that's why, so you have 2 valleys and 2 species of spins, and therefore you have 4 species. And so N is 4. And so you find out the denormalization of velocity and quasi-particle residue. Now, what is this quasi-particle residue? This is really for the beginners. I apologize to the experts. You see, when you write down a Green's function of a particle, if it's a free electron, your Green's function is just 1 over omega minus some k, okay? But now, then you have self-energy because it's not really a free electron, it sees other electron, and therefore, this interaction gives a self-energy correction. Now, if you expand this self-energy in powers of omega and k, you can write down the Green's function in this form, okay? And this Z inverse is called the quasi-particle residue. It gives you the weight of the Green's function around the pole omega equal to sigma dot k, okay, times z k. Now when this Z inverse goes to 0, your quasi-particle, when this Z goes to 0, your quasi-particle picture doesn't hold anymore. So this Z tells you, having a Z close to unity, essentially tells you that your quasi-particle picture holds, and having it different from 0 essentially tells you that your quasi-particle picture is not valid and you shouldn't be doing this calculation. So it's an estimate of telling you whether this single particle Green's function works. So now, using these renormalization techniques, what does this renormalization do? It tells you that suppose you start with a given energy and you have a given velocity and this quasi-particle residue Z in that energy, then what it tells you is that if you lower your energy a little bit more and you want to maintain the same form of this graphene Hamiltonian, how the parameters change. Okay, and this lowering and this flow of this change in parameters is essentially characterized by something called L, which is typically called the RG time, or the renormalization group flow parameter. So essentially what you find here is that this renormalization group predicts to an unstable fixed point at a critical value of 0.8. Okay, so this is an analysis whose numerics is not to be taken very seriously, but it tells you that the graphene should go from a weakly interacting regime which supports quasi-particles to a strongly interacting regime which doesn't support quasi-particles at around alpha equal to 1, okay, of the order 0.8 or something like that. And we are sort of below that threshold. So we can still think of, graphene to be Fermi liquid in this sense. However, there are changes. Now, any of these quantities now receives correction due to this electron-electron interaction, and anything that you measure, like compressibility, diamagnetic susceptibility, specific heat, quasi-particle lifetime of graphene, essentially now has these logarithmic corrections that comes in because of this electron-electron interaction. But thankfully, this is a log correction, and therefore, for any finite kf, that is any finite value of the Fermi energy. So if you are just a bit away from the Dirac point, this is a small number, okay, because it's log, and therefore, qualitatively, of course, things remain the same. However, something very interesting happens, and that happens when you consider the renormalization of the Fermi velocity. The Fermi velocity, of course, for graphene, it shows a peak like this near the Dirac point because the density of state goes to 0 at that point. One can relate that to this divergence of Fermi energy. Typically, this is supposed to be linear, but now we have a conical singularity out there, which is shown in this figure B in the right side. Okay, and this conical singularity is something that Andregain's group essentially pointed out, and this qualitatively at least matches this expectation. So typically what you see is, for example, the specific heat was supposed to have a t-square behavior if it's a standard non-interacting electron, but now you see that it has a t-square behavior along with this log factor. Okay, so for example, okay, so these are the changes that comes in due to electron-electron interaction. Another thing which comes in is collective modes. In graphene, it turns out that the interaction gives rise to collective modes, which has omega equal to square root of Q dispersion, and that is the standard thing that you find for any 2D electron gas. Okay. But there is a difference. So the thing is that if you have undoped graphene, okay, so when you have a collective mode in either 3D or 2D material, what happens is that the collective mode essentially derives from the fact that there is a finite density of state around the Fermi surface, where which puts weight to the velocity of this collective mode. Okay. So in 2D, typically these collective modes go as omega times some constant, omega equal to some constant times root Q. At low energies, but however, this constant depends on the density of state. And therefore, if you don't have any density of state, which is the case around the Fermi surface, which is the case for undoped graphene, then clearly you don't have a collective mode. Okay, and in this case, you have you also do not have intraband transition, because you cannot really have transition between these two modes at the same Fermi at the same Dirac point. But you can have transition between K and K prime points, and those are the interband transitions which occurs when omega is greater than V times Q. Okay. However, if you have a doped graphene, then you can have both intraband and interband transition, and there is this collective modes. Notice that these collective modes enter the quasi-particle continuum, and this is where you have this phenomenon of Landau damping. That's a standard 2D physics, and this is something that is expected in graphene. Okay, I'm not going to get into the details of this, but let me just end this part by saying that people have looked into the fate of graphene in the presence of strong inter-site potential. That is, if you take the graphene thing and just put a Hubbard-like interaction on this, just to understand when the metallic phase, okay, of graphene, the Dirac metal phase, or which is typically also called the semi-metal phase, this Sm, gives way to strongly interacting phases which are gapped. And it is seen that you can have nearest neighbor interaction, which is this V, and on-site interaction, which is this U. And as you increase this U or V, you go either into a charge density wave phase, where if V is strong compared to U, or into an antiferromagnetic Hubbard-like phase if U is large compared to V. Now, apparently, it turns out that the critical U, so suppose I said V to 0 and only put U, the critical U C, this U C for transition from a semi-metal to an antiferromagnet is typically U over T equal to 5, and that's a very large on-site interaction. Okay, so there are these transitions, and this is an interesting phase diagram. But for the rest of this lecture, what we are going to assume is that the graphene is still in this metallic phase where Fermi liquid theory holds, and we are going to only be concerned about quasi-particle properties of graphene. Okay, and see how Dirac physics manifests itself in properties of graphene, things which are not typically seen in conventional 2D metals. So, any questions regarding this? I think I should just pause for a bit and ask for anyone has any questions? No? Okay. If not, let me just go over. And so to summarize this part, so the interaction effects in graphene are there. Okay, it's not non-interacting, but they come through some logarithmic terms which are incredibly small usually, and therefore there is no qualitative difference between this graphene, non-interacting graphene quasi-particles and interacting ones. However, certain things shows up. For example, if you are really close to this Dirac fermions, the Dirac points, then what happens is that there is a conical singularity in the Fermi velocity. Okay, instead of having a straight line, standard linear singularity. However, and also the fact that there is a Plasmon mode which goes as square root of Q. At this point, I'm going to also mention another thing which we are not going to be concerned much. Two things. One is, well, let me just mention one. So the thing is that when we talk about graphene samples, these are intrinsically disordered. Okay, and this disorder becomes significant when you try to go near the Dirac point, because near the Dirac point, the density of electrons is small. So the relative density of disorder versus electrons really increases. Okay? And what that means is that the system is going to be very strongly disordered if you are sufficiently close to the Dirac point. And this results in formation of patches of, so in the presence of that kind of disorder potential, what happens is that the electrons goes through a phase separation. They become concentrated in puddles or in regions of space where there are larger electron density compared to other regions where there are smaller electron density. So this thing is typically called puddle formation in graphene. And this kind of puddle formation mostly gives a completely different experimental signature of many things when you are, such as conductivity, etc., when you are close to the Dirac point. However, if you go away from this Dirac point and you have a finite density of state, everything is okay, because disorder density becomes small compared to electron density, and in that regime, this puddle formation doesn't play a substantial role. Also, as opposed to graphene on substrate, you could put freely suspended graphene, and those are much cleaner sample, and there this puddle formation effect is reduced. Okay, so we are not going to talk about this puddle formation anymore. And just to mention that the theoretical treatment of this puddle formation is extremely complicated, and it's quite tenuous. Okay. So okay, so this is it. So now I'm going to talk about, if there are no further questions, I'm going to talk about transport properties of graphene. So anything which is unclear, any questions? Okay, if not, let me try to go to these transport properties. Okay. So transport properties of graphene, and particularly I'm going to talk about transport junctions, can be understood in very simple terms. Okay, if you consider ballistic junctions, okay, which means that you are not going to consider disorder, but you are just going to allow for the electrons to freely move in this graphene in the presence of an electric potential. Okay. So these kind of things are related to a problem in quantum mechanics, which we calculate in our first course in quantum mechanics. That is scattering of electrons from barriers. Okay. And I'm going to tell you why these are related in just a few slides. But let's just look into potential barriers for electrons. So suppose we did this for the electrons, which follows the Schrodinger equation. Okay. So what do? We put in a barrier over a region in space, and we ask the simple question that what's the probability of an incident electron to penetrate through the barrier? Now here, it is probably the first time that we encounter the difference of quantum mechanics with our standard intuition. So imagine, and that happens when you target an electron or a particle with energy E, which is lower than that of the barrier. Now, if you take this problem to the classical world, this is like throwing a ball at a wall. And as long as your starting height for the ball, as long as your starting height of the ball is lower than that of the height of the ball is going to strike the wall and it's going to come back with unit probability. It's not a probabilistic thing, it's a deterministic thing, and the ball will always come back. However, quantum mechanics tells you, and this is something that we work out, that even if the energy of the particle is small compared to that of the height of the barrier, there is a possibility that the particle is never going to be reflected back. It's going to transmit to the other end, and this phenomenon is known as tunneling. Okay? Tunneling is an intrinsically quantum effect, which we see in our first quantum mechanics course. So this tunneling, essentially, one can calculate the probability of this electron to tunnel to the other side, and it turns out that this quantity depends on a dimensionless barrier strength, which is given by 2 times V naught times d divided by h bar Vd, where Vd is a typical velocity scale that you create out of this problem. It's h bar divided by the mass of the electrons and the thickness of the barrier, whereas this V naught divided times d is essentially the strength of the height of the barrier times its dimension, okay, the extent. So when this chi is large, that is when the barrier is, this dimensionless barrier strength is large, you see that the tunneling exponentially decays with the barrier strength. Okay? With V naught minus E, that is, so I can say that when the energy is small compared to the height of this barrier, the tunneling is going to exponentially decay, and it's a monotonically decreasing function of this dimensionless barrier strength chi. Now, this gives you some sort of intuition regarding this, that, okay, maybe something strange happens when the energy is not so small compared to the barrier, but nevertheless, this probability of tunneling does decrease exponentially when my barrier is large, and maybe this is one way to reach the classical limit. Well, that intuition completely goes away when you consider the same thing with a Dirac electron. So this is another thing that all of you can work out. Just take the graphene electron, okay, and I already showed what the Hamiltonian of this graphene electron is. It's just some sigma dot k, and solve this barrier problem. Okay, and this is a really simple problem because you just have to match wave function continuity at the 2 ends, okay, and calculate what the transmission probability is, and that's a reasonably simple calculation. But when you do that, and in the limit where this barrier potential is large but the barrier extent is small, it's typically called the thin barrier limit. That is that the barrier is thin but it is very, very strong. Okay, so V naught is taken to infinity and d is taken to 0, with this V naught d divided by h bar Vf held fixed. Okay, so that's the dimensionless barrier strength. So you find that in this limit, the transmission probability goes as cos square gamma divided by 1 minus cos square chi sine square gamma, where gamma is the angle at which this electron approaches the barrier. Okay. It's tan inverse of ky over kx. So in my picture, the barrier is along x, and the electron approaches this with an angle theta, and that theta, or what I have written gamma here, is tan inverse of ky over kx. Now, this expression is funny for two reasons. The first one is that suppose my gamma was 0. Okay, that is, I approach the barrier perpendicularly, normal. Okay, this essentially tells you that irrespective of what the value of chi is, no matter how strong the barrier is, your transmission is just 1. Okay, this is clearly a paradoxical result. How can an electron not get reflected, even if you have a very large barrier? Well, this was noted by Oscar Klein right after Dirac equations were written down, and it goes by the name of Klein paradox. And here I have just modified it for massless Dirac electrons. Klein's equation was for massive Dirac electrons, but it's the same thing. So there is one way of looking at it. Why you do not have a reflection when the electron is approached, when the electron approaches the barrier normally. The reason is that, remember that this electron is a property of helicity, which means its spin, or in this case pseudo spin, that is its probability to be on the A or the B sublattice, that essentially points towards this direction of motion. So if it points towards, for example, if it moves to the right, which means it's going with kx equal to 0, it means that it's in an eigenstate of sigma x with eigenvalue 1, which means that it's in an equal superposition of A and B sublattice, okay, with a relative phase 1 between the two sublattices. Now, if the electron gets scattered from this barrier, its direction of motion is reversed, which means that its pseudo spin, which must point because of the helicity property to its direction of motion, must get flipped. However, this electron that I have put in has equal value of B naught on A or B sublattice, which means that in pseudo spin space, that is in the AB space, it's a scalar potential. And we know from our basic scattering theory that scalar potentials cannot flip spin, or in this case pseudo spin, upon scattering. So if the electron approaches normally to the barrier has no choice but to let the electron go, because any scattering which is flipping of this direction of motion is also going to require flipping of the pseudo spin, and that the barrier cannot do. Okay. So this is the explanation of this Klein paradox. The second thing which is interesting, and this is another property of this Dirac fermions in 2D, is that if you put in chi equal to n pi, that is, if your dimensionless barrier strength is an integer multiple of pi, your transmission again becomes 1, and this is called the transmission resonance condition for Dirac electrons. So the basic point is this transmission is an oscillatory function of the dimensionless barrier strength. It's not exponentially decaying or a monotonically decreasing function of this barrier strength. And therefore, the transmission or ballistic transport is expected to be qualitatively different in this kind of materials compared to that in in standard electrons, where standard metals, where electrons obey Schrodinger equation. So, is this point about transmission clear? Any questions?
Sir, it is not clear to me why this flipping of pseudo spin, that is not possible only for this normal incidence. I mean, why not in other kinds of incidence? We still would have the electron traveling in some direction, and there would be some pseudo spin associated with it. Would the barrier be able to flip that?
That's because that's because in that case, when the electron is reflected, the pseudo spin do not completely flip. It just changes an angle. Can you see that?
I see. Okay. Okay.
Okay, so and that's why there is a finite overlap between the reflected wave function and the transmitted wave function.
Okay. Okay.
Okay, so and that's why normal incidence is special. That's a very good question. And so, you know, you are going to see this if you just at some point work out this problem. Another thing that I'm going to point out since you asked this question is that while working out this problem, you are going to see that there is another difference. That is, when you work out this kind of barrier problem, what you do is that you equate. So if you have a finite barrier like this of different thickness, at each edge of this barrier, you typically equate the wave function because there should be continuity of waves and also the derivative. Okay. And why do you do that? Because Schrodinger equation is a second order differential equation in second order spatial derivatives, right? However, here it's a two-component Hamiltonian. Graphene is a two-component Hamiltonian, but it's a linear equation.
Right. Right.
To only equate, ensure continuity of the wave function, and that's all.
Right.
You don't have to equate the derivative of the wave function. There is no condition on the derivative. And you could have this kind of oscillatory behavior as opposed to the standard, you know, the monotonic behavior. And this comes out from the math if you do it. Okay.
Okay.
Okay. Any other questions? Okay, if not, let me just go ahead. So now I'm going to sort of tell you about a story which we were a part of, in which case apparently we found out how this basic physics manifests itself in tunnel junctions in graphene. So apparently, before going into the graphene part of it, let me just talk a little bit about these tunnel junctions, which is a standard thing that people have in condensed matter when they measure, you know, tunneling conductance and stuff like that. So you see, if you take two pieces of metals, okay, which is right here, and this is something that I probably have already told you in the first lecture while discussing superconductivity, but let me just go through it once again because this is important. So if you have two pieces of metal separated by a barrier, what happens is that your electrons can go from the left to the right if you put in a gate voltage. And so you put in a voltage, you see a flow of electrons, and that's your current. And then you take the derivative of that current with respect to your voltage, that is dIdV, and that's your tunneling conductance. Okay. So in experiments, you measure either put in a current and measure the voltage, or you put in a voltage and you measure the current. Okay, it depends on what you do experimentally. But at the end of the day, you see how the voltage changes with respect to the current, or other words, and dIdV gives you the conductance. In superconductivity, you really cannot do that because there is an energy gap for this Bogoliubov of quasi-particles, and therefore, if unless your applied voltage is larger than that of the gap, you find that you cannot push a current through. Now, normally, this is not the full story. What happens is that because it's a superconductor, as we saw in the previous discussion, I think in lecture 1, there is a mechanism called the Undo Deflection, where if you push in an electron in the system, you could get back a hole and two electrons. So what happens is when you push in this electron, electron hole quasi-particle, that is a Bogoliubov quasi-particle, pops up from the superconducting vacuum, and the hole comes out, the electron pairs with the incident electron and goes on the other side, and that leads to a quasi charge transfer. This phenomenon is known as Undo Deflection, and this Undo Deflection is how a superconductor conducts current at almost zero applied voltage. Okay. However, if in a tunnel junction, the barrier potential that you have between this normal metal and superconductor, you know, if that is large, then the amplitude of this Undo Deflection gets killed very fast. Okay. So, for example, if you take a dimensionless barrier strength, which characterizes this barrier I as Z, and if you go from Z equal to 0 to large Z, you see that the tunneling conductance inside the gap, which is due to the subject process, dies down very quickly. Okay? And apparently it dies down as 1 over 1 plus 2z square whole square, that is as 1 over z4 in the limit of large Z. And this is something that one can show. Okay. There is a classic paper by Blunder, Tinkham, and Klavzik which has done this analysis, and this is something that you can go through. But the point is that in the limit where there is a large barrier strain, you see this tunneling conductance just tells you about your superconducting gap, stating that typically as you increase your Z, your tunneling conductance is going to be a monotonically decreasing function of the barrier strain. And this is a property of any normal metal superconductor junction. So as you increase your barrier strength, if your voltage is sub-gap, that is if the voltage is less than the gap of the superconductor, with increase in the barrier strength, you essentially kill the tunneling conductance within the gap. So it's a monotonic function of the barrier strength. Now, we wanted to look at this when you do this with graphene. So graphene is not a normal, graphene is not a superconductor standard this thing. But what you can do is that you can bring a superconducting electrode very near a part of this graphene samples shown here. And then superconductivity, standard SOF superconductivity is induced in graphene by proximity effect. So this is a phenomenon where if you bring in a metal or an electrode of a metal which is superconducting, okay, close to another metal, the first electrode essentially induces superconductivity on the second. A similar thing can be done by a magnetic sample. So if you bring a ferromagnet, for example, very close to a metal, it induces magnetism. And this type of induced superconductivity or magnetism or whatever is induced is called proximity induced either superconductivity or magnetism. Okay, here we are going to talk about proximity induced superconductivity. And this happens because at some level, because the wave function of this superconducting electrode now has because of the proximity to the graphene sample, has a direct overlap with the graphene wave function, and that's how it induces this superconductor. There is a whole class of theory which is being developed to explain this proximity effect. I'm of course not going to get into the details of that, but we're going to just note that if I bring a superconducting electrode very close to this graphene, then one can induce superconductivity. So this is the superconducting part. The rest of this graphene sample is kept normal. Okay. And in between, we have thought of putting in a bias voltage V, which acts like a barrier potential. Okay. So this voltage essentially creates a difference in electron density in this region I and this region N, and this electron, which means there is a mismatch of Fermi surface between the two regions, and therefore this acts as a barrier, okay, for the electrons to go in from the normal to the superconductor. Now the question that we asked is that how would the tunneling conductance of such a junction behave as a function of the gate voltage? Now, normally you would say, well, we know how tunneling conductance of normal metal superconductor junctions behave, and it just goes down if you increase the barrier strength. However, here we are dealing with graphene electrons, and a qualitatively different thing happens. However, before doing that, let me just try to show you how this calculation is done. So what one typically does is to imagine that a quasi-particle approaches this barrier or this insulating regime from the left, from the normal region, and then it can get reflected or it can get reflected, and there is an amplitude of transmission T and T prime into the superconducting region. Okay, so the electron wave function, that is the quasi-particle wave function in region 1, has an incident electron which is psi m e plus, a reflected electron, which is this reflected part, which is psi En minus, because it moves in the other direction, and then oppositely moving hole. Okay, and that's because there is a superconductor on the other side, and the hole may come out because of this Undo process. So the amplitude of this reflection is called R, and the amplitude of this Undo reflection is called RA. Okay. In the superconducting region, there may be right and left moving quasi-particles, and that's the wave function of those are psi s plus and psi s minus. And in between, you could have right and left moving quasi-particles, which might be electrons or holes. So there may be right moving electrons or right moving holes with amplitudes, P and M, and left moving electrons and left moving holes with amplitudes Q and N. So what do? We now match these boundary conditions by demanding continuity of the wave function at this edge, which is the left edge, which is situated at x equal to minus d, and the right edge, which is situated at x equal to 0. And we obtain the values of R and RA from this. And then the transmission probability is 1 minus the total reflection probability, and the reflection probability is mod RA squared, okay? Because if an electron comes out, then of course, it's reflected. But if a hole comes out in the other direction, you have to add that amplitude to the conductance, because a hole coming out of the other direction essentially means 2 units of electron charge has gone in. So the total transmission probability is 1 minus mod R squared, which is like the standard thing, but then you have to add the amplitude of this Undo reflection out here. Okay. Now, after you have done this, you are of course going to do this for a fixed angle of incident of this electron, which is a fixed transverse momentum. Okay. Then you are going to sum over all transverse momentum, which is this integral in my case, and then multiply it by the unit of conductance. And that's your total conductance. And because conductance is just the transmission probability in every given channel, which in this case is every angle of incidence, and summed over all channels and multiplied by a proper E square over H, which is the unit of conductance. So essentially, this formulation is essentially due to Landauer and Batiker, and it's called the Landauer-Batiker formulation. But the point is that once I know the transmission, I know the conductance from this, okay, up to an integer. So how does this conductance look? Now, what do I expect? As I change my gate voltage, which is this Vg, as I increase it, for standard electrons, I'm going to get a monotonically decreasing function of the barrier strength. Okay. However, what we found is that in complete contrast to all known results for Schrodinger electrons, this graphene electrons essentially shows a pi periodic oscillatory behavior. Okay. And that was what we looked at. Essentially, so if you fix your applied voltage to very close to 0, that is, if you are right in the middle of the gap, you find that as you increase this tunneling conductance, you are supposed to, as you increase this barrier potential, so this is now dimensionless barrier potential, which is this Vg in dimensionless units. Okay, this I is Vg times d, which is the thickness of the barrier divided by h bar Vf. So you see that there is this oscillatory behavior. So normally for Schrodinger electrons, as you increase this psi, you would see that there is a monotonically decreasing barrier, the transmission coefficient or conductance. However, here it just oscillates. Okay. Now you could do this not only for the thin barrier limit, where this oscillations essentially has a pi periodicity, but you could do this for any barrier limit. And you see that the period of this oscillation still persists. However, the period of oscillations widens and its amplitude decreases as you increase the thickness of the barrier. So this unconventional oscillatory phenomenon is a manifestation of Dirac quasi-particle behavior. And to understand this, we found out that if I am at sub-gap voltage, EV much lesser than EF. So this will clearly hold when the voltage, applied voltage is 0, for example. Okay, then I can have an analytic expression for the reflection probability. Okay. Now clearly, since my tunneling conductance is 1 minus mod r square plus mod r square, the maximum of tunneling conductance is going to occur when r is equal to 0. And therefore, if, and just look at this, so if the maximum occurs when r is equal to 0, this tells you that the 0 value of r, that is the reflection probability, must also be a periodic function. Okay? And this is precisely what you find, that this has a sinusoidal character with this dimensionless barrier potential. Okay, so if I try to analyze this, where does r goes to 0 when the barrier strength, when the tunneling conductance is maximum? Well, it goes to 0 if you have normal incident, and that's because that's a manifestation of Klein paradox. You remember that we told you that if an electron moves, approaches a barrier in graphene, perpendicular to the barrier, it cannot get reflected, and that's this factor of sine gamma. However, this is not the main thing here, because this just goes to 0 when there is normal incidence. The tunneling conductance, on the other hand, is a sum over all angles of incidence, and this is just a point in that sum. So it doesn't really make that much of a difference. It also goes to 0 when beta is equal to 0. That is when the applied voltage is equal to the gap. Okay, EV is equal to delta naught. But that is known from standard theory of superconductivity, and it's called the Coherence Phenomenon. But I'm not going to get into the details of that. But all I'm saying is that that's not anything new because of graphene. It's standard superconductivity. But what is new here is that there is this chi dependence, and you see that when chi is equal to n plus half times pi, okay, this difference of these two signs go to 0, and therefore and you have this pi periodic oscillations. Okay? So again, the probability of reflection is a dimensionless number in terms of this barrier strength, and we have dimensionless barrier potential out here. Okay. Next, let me move on to Josephson effect. Okay, this is another interesting thing that happens. So, okay, but before I do that, any questions? Anything which is unclear? Okay, if not, let me go into this Josephson effect, and I should probably hurry up a little bit. So you see that just as you are putting this induced superconductivity on one end, you could have done this with two ends, and then you have a superconducting, insulating, superconducting barrier, which are good for studying Josephson effect. And this Josephson effect comes in when you put two superconductors with different phases right next to each other. Okay, and the ground state wave function on the two parts of these superconductors is phi 1 and phi 2, and therefore at the boundary you have a gradient of this phase. And what Josephson showed is that once you have this gradient of phase in a superconductor, you have a current, and therefore putting these two superconductors on top of each other gives rise to a current. Okay, and that's your Josephson effect. So when you do not put any voltage to this, then it just depends on the phase difference, and that's called the DC Josephson effect. Now, these Josephson junctions are of two types. One of them is called weak links, where these two superconductors are separated by a metallic junction, and this is something I'm not going to talk about. I'm going to talk about what are known as the tunnel junctions, where these two superconductors are separated by a barrier potential. Okay. This means that So the point is that in this kind of tunnel junctions, what we find is that the Josephson current can be understood as due to formation of localized quasi-vertical subgap state in the barrier. So what happens is that when you put in these two superconductors right next to each other, apart from the standard states that you have in each of the superconductors, in the barrier region, you have some additional states which are localized in the barrier. They decay as you go in either within superconductor S2 or within superconductor S1. But most importantly, these are the only states which depends on the phase difference between these two superconductors. And therefore, they contribute to the Josephson current in spite of being localized states. Okay, and you can think of why that is the case, because localized states usually do not carry current. And I'm going to leave that question for your thought, but that's a food for thought. Okay. Maybe if you think about it this a bit, and if you don't know this in the next lecture, I can talk about it. But let me proceed now. So apparently, this energy of these bound states can be easily calculated, and it depends on the transmission probability. There is the transmission of this barrier. So Z is the dimensionless barrier strength, and this transmission goes to 1 when Z goes to 0. And that's the limit of a transparent barrier. That's called the Coulomb-Chuk limit. Out of the in the name of two Russian physicists who first came up with this. And then if Z is very, very large, you find that transmission tends to 0. It's not quite exactly 0, but it's roughly 0. Then this is called the Ambegaoker-Baratok limit. For the Coulomb-Chuk limit, I'm going to concentrate on the Ambegaoker-Baratok limit, for which this transmission goes as T sin phi. Okay. So typically everywhere, as you go from this Ambegaoker-Baratok to, Coulomb-Chuk to Ambegaoker-Baratok limit, you find that as a function of this increase of decrease of T and increase of Z, as you go from this Coulomb-Chuk to the Ambegaoker-Baratok limit, the critical current of this junction, which is the maximum current that this junction can have, as well as the current in general, is a monotonically decreasing function of the barrier strain. And again, when we do this for graphene, what happens is that this becomes, because the transmission becomes an oscillatory function of the barrier strain, this also becomes an oscillatory function of the barrier strain. And typically, this is also the Josephson current in this kind of junctions also will have this property. And okay, so I don't want to get into the details of this, but the point is that instead of having a monotonically decreasing critical current in these junctions, you are going to see an oscillatory one. Okay? And that's the typical thing for this kind of Josephson junction. Again, different from standard metals. So this is what I wanted to tell about transport, or ballistic transport in this kind of materials. And the next question that comes, which I'm not going to address, is what happens when you put in disorder. Well, the point is that for weak disorder, nothing much, because these type of materials do not localize very well. So typically in two-dimensional standard metals, from this really nice work by T.V. Ramakrishnan, Lee, Anderson, and others, and Elio Abrams, that typically two-dimensional metals just localize even if you put in a weak amount of disorder. But that's for conventional Schrodinger electrons. For graphene electrons, they belong to a different symmetry class, and they do not localize, and therefore a little bit of disorder doesn't do much. Okay, so this this ballistic regime extends for weakly disordered regime as well. It's only the amplitude of the current that decreases with increase of disorder, but the phenomenon is qualitatively lowest. Okay, so any question regarding this transport part? If not, I'm going to go into the next part, which is edges and impurities. Anything which is unclear? Okay, if not, let me go into the next part, which is this edge physics in graphene. So graphene, of course, is a two-dimensional hexagonal, two-dimensional honeycomb lattice, but it does have its edge. And there are these two types of edge. One of them is called the zigzag edge, which I am going to concentrate on. and the other one is called an armchair edge. So let me try to show some plots here. Yeah, so you see that this is called the zigzag edge of graphene because the graphene atoms here goes in this zigzag manner. And this is called the armchair edge where there is two atoms, a gap, and two more atoms, another gap, and so on. So I'm going to talk about edge physics in case of this zigzag edge. So it turns out that the graphene electrons in this zigzag edge essentially allows for zero energy states, okay? Which by itself is interesting phenomenon. But why does this state occurs? So imagine that for this kind of states to occur, what I need to have zero energy states. You see that if I concentrate on this site, okay, then from this side I can hop on to this the two neighboring sites, and then on a site which is directly below. Now the understanding is that if the total Hamiltonian, that is the total energy coming from all these three hoppings, essentially adds up to zero, then I can have a zero energy state. But that's not going to be possible if it happens only for this site. It also has to happen for a site here, and also has to happen for the site here, because the wave function should be consistent at every place. So what do we need? We need that the hopping from this site out here, which is x plus e to the power I k n out here and e to the power I k n plus 1 out here, they should go to 0. And then this one should go to 0, and also x plus y plus z should go to 0. Okay? So these hoppings should all go to 0. And it turns out that there is a consistent solution for this. And once you put in this solution, once you solve this, you find out what this x, y, and z are, and you see that z, which is at the second layer, essentially goes as cos squared. The x and y, which are in the first layer, goes as a cosine, and this is of the order 1. Okay, so the decay occurs with an amplitude which is mod 2 cos k by 2. Okay. And since the decaying solution requires that you should have this quantity less than 1, and that this should be negative, okay, this means that for k between pi and 2 pi by 3, you are going to have this zero energy state. So this tells you an analytic solution for semi-infinite states in graphene, which are localized at the edge because they decay as you go in the bulk, and they are of zero energy. But this is just standard analytics, but you could see those numerically also. What people did is that they took ribbons, which are long chunks of graphene sheet, which is elongated in one direction and has two edges close to each other in the other. And they found that when they looked into these ribbons, they found there is some finite density of state at zero energy, and they also checked that these states are localized near the edges of the sample. So those are your edge states, okay? And these edge states are for real. But the interesting thing that happens, that comes from these edge states, is that you get some magnetism at the edge. And why is this the case? Now, if you put in some interaction, okay, these states, okay, so one thing that I haven't told you is that these states have all amplitudes either on the A or the B sublattice, but not both. And this means that they are in the eigenstate of, so pseudo-spin state of sigma z, okay, either +1 or -1. This also means that if you put in an interaction string, and because graphene lattice is bipartite, by a theorem of Leib, you could say that, well, this must come with an inbuilt magnetization, because Leib showed that if you have on-site potential on a bipartite lattice in one dimension, the state must have a magnetic character, and the net magnetization is going to be net magnetization is going to be the difference between Na and Nb, that is the occupation of the A and the B sublattice of this bipartite lattice. And so here it is maximally magnetized, and that's the ferromagnetic state. And this indeed is verified by DFT calculation, and they showed that you have this net magnetization at the edge of the sample. Okay. So, any questions regarding this? Is this point clear?
Sir,
Yeah.
yeah, I could not follow this the argument by Lieb that I mean
Well,
by
I haven't really given you the argument. It's just a statement. You see, one dimension there is so what Lieb said is that if you have sorry, not in one. So if you have a bipartite lattice, okay, and Hubbard model on that lattice which of spinful electrons, in the limit of really strong interaction, which is the case here because your kinetic energy is 0 for these states, okay, you're going to have a ferromagnetic state where the total magnetization is difference between the occupation of A and B sublattice. That's just a statement. I proved it for you, but if you look into this paper by Lieb in 1989, paper here because it's on web and it's not really on archive. But if you look into this paper, you're going to see the proof of this, which is very complicated. But the point is, if we take that result, we know that here we are going to have such a ferromagnetic structure. Okay, zero energy state, and therefore any U is like infinite interaction. And it's the state is localized either on A sublattice and B sublattice, so it has a finite S, which is A minus NB by 2, and therefore it has this ferromagnetic state. There should be magnetic moments localized at the edge of the sample. Okay. Yeah. Sorry, this is not so easy to explain exactly why this happens. It's a pretty complicated reasoning and calculation. Okay, you really need to look at Lieb's paper.
Hello, sir.
Yeah.
Sir, why that magnetization is properly localized in the edge?
Oh,
I didn't quite follow.
Okay, one way to understand this is that when you go deep inside the bulk, these zero energy states decay, and also in the bulk, it's equally distributed between A and B sublattice. So this spin is 0. Now net magnetic moment is 0. And we know that it's a non-magnetic state.
Yes, sir.
Okay. Any other questions? Anything which is unclear? Okay. If not, let me go to the last topic of today, which is this Fetal Oscillation. And here, I'm going to sort of talk about what happens when you put in an impurity on top of this graphene. Okay. So imagine that you have this graphene honeycomb lattice, and you put in an impurity on top. So now this impurity can sit right at the center of the hexagon, or on the site, on one of these atom site, or essentially it can also sit on one of these links. Okay, it can be anywhere. But and what we are going to see is that because of these Dirac electrons in graphene, it turns out that the position of the impurity matters. Okay. Now the first is, what is Fetal Oscillation? So this is an effect which was first discovered by Puddle and also Noziers at some level. So what happens is that if you take a conventional metal, which has electrons around the Fermi surface, and you put in impurity, this impurity leads to a scattering potential. Okay, so the electron gets scattered of this impurity. Okay, and therefore its density of state changes around the impurity because it can get scattered. Its density of state changes. Now, if you look at this density of state as a function of position from the impurity, what Friedel and Noziers showed is that it has an oscillatory part which depends on cos 2kf r, kf being the Fermi momentum. Okay, so it oscillates with a typical characteristic wave vector which is 2kf, and that's because in a typical Fermi surface, this impurity scatters this electron from one point of the Fermi momentum to another. So it's a 2k distance. However, there is also this thing that as this oscillation, it decays as you go away from the impurity. And in 2 dimension, this decay is typically 1 over r. Okay. So Fetal oscillation in 2 dimension tells you that the density of state as you go away from the impurity center should go as 1 over r times cosine of 2k. Now people address this in graphene by using some technique which I am not going to get into. There is some typical formalism called the Kinetics Formulation. This typical scattering theory, which is basically generalized for taking into in this many body context. But the interesting thing that happens here is the following. You see, it turns out that graphene has 2 values, right? One around the k point in the Brillouin zone, and the other around the k prime point in the Brillouin zone, right? So if you put in an impurity, there can be 2 types of scattering. One of them is where the electron scatters from one Brillouin zone to another momentum which is in the same one point in Brillouin zone to another momentum which is near that point. So k to k scattering, and that's typically called an intra-valley scattering because it retains the electron within the same valley. And then there are these inter-valley scatterings which really takes a momentum k to momentum k prime. Now the second, this inter-valley scattering is the conventional scattering, and it does give you this cosine, this kf is just your omega by v. So this cosine divided by r, that's a standard scattering, the standard density of state dependence that you get from this inter-valley scattering. That's just like a 2-dimensional electrons. But if you have intra-valley scattering, okay, this is not, so what happens is that the electrons can scatter also from one point of the Fermi surface in a valley to another point there. But if that scattering is, like if the amplitude of that scattering is calculated, you find that there is no 1 over r dependence here. It turns out that there is an exact calculation of this 1 over r terms, which comes from the scattering amplitude coming from the A sublattice and the B sublattice. Okay, it just happens that way, and therefore this quantity goes as sine 2 omega r by r squared. Importantly, this is an r squared thing. Now, if you look at the first Fourier transform of these quantities, that is the Fourier transform of this, rho n, if this quantity dominates, you are going to see a completely different behavior because of this 1 over r behavior compared to this 1 over r squared behavior that happens. And these first Fourier transforms are calculated, and people see that if the graphene electron is in the center, then they see a behavior like this, where the scattering of amplitude is large at small momentum, and it decreases very fast as you go out. And another when it's on site, where this is small at the center, but it increases as you go out. Okay? Now these two can be related to a 1 over r dependence, which is typically when the graphene impurity resides on the graphene electron on site, and a 1 over r squared dependence, which typically shows up when the impurity electron resides on the center of the lattice of the graphene hexagon. Okay. And this phenomenon, this position dependent change in the density of state of graphene electrons in the presence of an impurity, is another signature of this Dirac-like behavior, because this 1 over r squared behavior requires a Dirac dispersion and intra-valley scattering. Okay. So that's the point. So what we find is that this Dirac nature of graphene electron changes the Fetal oscillation behavior, a decay from 1 over r to 1 over r squared. And this is some experiment that is done in Bari Monoram's lab, where they could measure this r dependence of this density of state in real space. And you see that when they compare the graphene thing with the copper thing, you see that there is a distinct difference between how fast it decays with increasing R, and graphene has a much stronger decay, which they fitted to a 1 over R square, whereas the copper one has a 1 over R decay, which is standard two-dimensional stuff. Okay, so this is a copper thing, of course, and that's why it's a two-dimensional thing. So, okay, so I'm not going to take over Kondo effect today, maybe tomorrow, and that will be the last topic in graphene that I'm going to cover, and then I'm going to move over to topological insulators. But at this point, let me stop and take any questions that is there. Okay. Any questions? Okay, I think there is something in the chat box. Let me try to see what that is. Okay, this is really tricky to,
You want me to read it for you?
no, let me try to get this. Yeah, now I think I...
Okay.
Yeah, okay, great. Okay, the question is, in your case, for thick barrier tunneling conductance versus d over lambda f and v over mu naught plot, where mu n is mu s equal to 100 delta, so u naught is 0.1, okay? If the doping of this two region is not the same, then what happens? Is the oscillation there, or is there any cutoff? Well, okay, so there is a cutoff, but for all realistic cases where this two mu s and mu n are different, but a little bit different, you are going to have same qualitative physics, okay? It's just that the characteristic of the oscillations and their period changes a little bit. That's all that happens. And this is detailed in later papers which followed ours. I think I don't have it at the top of my head, but people looked into this. Okay, that what happens when you have different. So all this different chemical potential in the superconducting and normal region does is to provide an extra barrier-like stuff to the Dirac electron. Okay, if the Fermi energy is different in the two regimes, it's just like an extra barrier, and so it changes the oscillation frequency. Okay, any other questions? Okay, if not, I think I am done.
Okay. Okay, so then thanks a lot, everybody.